All right, guys. So basically, we got a few bad cells. I'm going to show you here by the test. This one is definitely bad. Sitting at 3.94 volts and 300, they look 4.22 volts at 13.34 ohms, but it dies quickly. We're gonna light her up. Let's see what happens when you make the cell combust. Ready? 3, 2, where are you going? Stay right there. Stay right there. You know what? Because it's no good anyway, so let's do this. Shit. Wow. I don't want that to happen. It's right there. Check that out, guys. That's crazy. Wow. That thing blew off like a rocket. Holy crap. That's crazy. And now I got to pick it up because it's burning my damn grass. Ah, come on, buddy. Get this out of there. Get this out of there, buddy. Red as a cherry hot bomb. Yes, sir. That's what happens to lithium. That's exactly what happens to lithium. See? Interesting. So while that one's doing that, we got a whole bunch over here that don't have any voltage. I want to see if they light up. So right now we have 0. I'm going to go ahead and put this here. And this battery's showing 0 volts. Let's see what happens. I try to reset the SID. It didn't work. Will it blow or is it completely dead? Let's find out. I got to figure out a better way to control this explosion. She did what I didn't think she was going to do. I want to keep this right here. Right. Elevate this like this. Okay. Actually worked just fine right there. Get this right here. There you go. All right. Let's see what happens. Ready? 3, 2, 1. Well, apparently that was, holy crap, that was still holding his watts. So that cell, wow, that's crazy. It was showing 0 voltage. That thing was fully charged, dude. So maybe the SID got busted. I'm not going to do the rest of them, except for the smaller ones here. And I got all these here. Got 1, 2, 3, 4. 4 of those, 5 of those, and then I have these small 18650s that are definitely garbage. Let's see what happens when I do this one. Will the same thing happen here? Let's find out. Nope, that one's dead. That one's dead. Nothing happened there. That one's dead. I imagine this one's dead as well. See? Oh, wait, wait. It's catching. It's catching. It's catching now. It is catching. This one's catching here. It is catching. I don't know if it's going to explode. We shall find out. Is she smoking? Oh, they're pretty much dead. I'm not doing that to these other ones. I'm going to try to repair them because these are brand new cells. Like literally, you could tell that I spot welded them, right? I'm going to bring these back to life. I have to remove the SID chip and replace it. That was a safe, fully throttle battery. And she's getting hot. She might discharge. Let's find out. Keep an eye on that. Well, there you go, guys. Reason why I did that, it's interesting to show you how much power this cell has. Okay? So imagine having a faulty BMS or having a faulty battery charger that keeps charging the unit and doesn't shut off, and having 30 or 40 cells together. Look at them. She's starting getting hot. She's about to take off. Imagine that escalating and blowing up inside your house. That is not cool at all, my friend. Dude, you took all the lights out of this thing? Look, she's getting hotter. Interesting. There she goes. She's getting hotter. Kind of weird the chemistry took that long, but she's going. Let me go put these guys inside because I will not sacrifice them now that I know that they're fully good. That's the SID. Probably blew its little fuse. Resistance. That sucker's getting hot. Will it combust? We shall find out. You guys are watching in the dark. Wow. Wow. I walk away and that happened. Check that out. That cell was completely dead, dude. I want to see if this one catches fire since we're already here. Oh, look, it's catching fire. Come on, buddy. Catch fire, buddy. The second one catch fire. That's amazing. That was a complete dead cell. I slapped it with an axe, cut it in half, and it took a while, and I started smoking. That is crazy. How dangerous. And the other one take off? Huh? Michelle, anything else explode? Oh. So there you go, buddy. That is interesting stuff. This one was completely damaged. And I believe it's still freaking cherry hot. This one's leaking. Might as well hit it with a torch and let it light up. Be back. That's just to show you. See it bubbling? They have liquid inside of them. There you go. That's the actual chemical. So, if it fully doesn't have any voltage in it, it won't ignite. But if you light it up with a torch, it does ignite. You don't want to be smelling that stuff, that's for sure. You have lithium, cobalt, magnesium. There she goes, there she goes, there she goes, there she goes. Might as well burn away, buddy. To me, I'm sorry, you might think this is wrong, but guess what? If I spent the money on a cell and I know it's bad, I like to see exactly what happens. You know, this is basically for educational purposes only. Don't recommend anybody doing this. Just think about it. That's one cell. The other one was sitting at 4 because I did charge it up to 4.22 volts. The other one didn't show no signs of any voltage at all, right? Put on a charger, doesn't show a battery at all. Try to push the SID in and it wasn't the SID. It was a brand new built battery that I built, and in a rush, right? I didn't do the correct sizing. I removed 30 pieces of it was originally a 10S 3P 42 volts 36 volt battery to 42 volts fully charged, and it basically had 7.5 amp hour battery pack. So I built a 15 amp hour battery pack, but I kind of rushed it a little bit, and when I forced it in, it arced, but not on the cell. It arced in the connection, of one of the strings, and 6 cells went completely bad. Well, now that we see they're not completely bad, they're just stopped showing. So basically, it probably burnt out, because you have the anode and the cathode, right? And it basically wrapped around, and it has a small little thin layer of aluminum, or a small little layer that comes from the big jelly roll of copper. You have the anode, which is a positive, and the cathode, which is a negative, and that's what makes the connection. That's why it's interesting how they're always telling us, well, if you're going to increase the voltage, they recommend, depending on how much amperage you're going to be pulling out your battery in continuous mode, you need better bus bars. You can't use this minimal 0.1 millimeter nickel, or 0.15 millimeter, 0.15 millimeter nickel, or 0.015 millimeter nickel, pure nickel. They recommend you to use 0.2 nickel, and then now they recommended you to use copper bus bars. But in reality, the cell itself, right, has a little string. I will demonstrate by taking one of them apart that it's completely dead, and we'll unroll it. I know you've seen it on YouTube. I just want to do it myself. Obviously wearing the proper gear, don't want to touch that stuff, and just show you how massive the roll is. Hence they get the power out of these cells. And you'll notice that when you buy these cheap cells, they sell on Amazon, where they claim it's an 18650 that has 8,000 milliamp hour battery, which is ridiculously a lie, because 18650 is the most they can go is 3,400, 3,500 milliamp hours at a low amp release, like the Panasonic's 8.9 amps, right? The trick with that is that you run a whole bunch of them in parallel, and you increase that total amperage, right? Now for high power cells, it's a 3,000 milliamp hour battery at 40 amps, 50 amp continuous. Ampus JP 30P1 is a good one to put in that situation. The Molacell P30B is another one, even though it doesn't give you the initial capacity, even running it at a 1 amp discharge. For full capacity, they claim to have 3,000 milliamp hours, and they have 2.8, 0.60 milliamp hours, versus when you do the JPs actually give you 3108 milliamp hours off a 3,000 milliamp hour battery. And even doing it on a high discharge, they still give you the capacity. One that I was really interested in, because of course, it's a weight factor. You weigh the cell. If the cell weighs light, right, you're not going to get that much out of capacity of the battery. Just plain and simple, right? Of course, the battery build, the way they build it, the way they laser attach those actual cathode and anode, the cathode's on the bottom, the anode's on the top. The whole cylinder itself is all the cathode, basically negative, until the top piece with a small little ring separating. But yeah, you get the weight. But I was very impressed with the Eve 30PL, because it weighed under, the Ampus JP 30P1 actually weighed. Like initially what it says on the data is exactly what it weighed. But the actual Eve 30PL weighed, I believe it was like 46.5 grams. And I did a capacity test, and it came out to 3168 milliamp hours. And then I put it on a full, because this claims to be a 60 amp continuous. I did put it with thermal checking it, make sure it reached, because it has a temperature cutoff of 80 Celsius, which is extremely hot, I believe. But it ran decent, and it gave me, at 40 amps, it still gave me 3,400 48 milliamp hours on 2 of them that I tested. Very impressed with the Eve 30PL. Don't know if you're going to get that in a long, cycle life, how many times you charge it, discharge it, because they do run a little lower. Ampus is pretty decent. It gives you a little higher on the main 5. They're not going to give you, on their data sheets, they usually say 3,000 milliamp hours. Minimum is 2,900 milliamp hours, right? But what you do get out of those cells, it's definitely a cell that lasts, if you're actually got a good BMS and you're doing the proper cycling and you're not completely discharging it to 2.5 all the time and, fully charging it to 4.20, you're keeping it in the medium area, the gray area where safety goes, and then of course, in running them in parallel, you get more if they claim like the Molocell P30V, I believe. It says, what does it say, 50 amps continuous, something like that. You're not going to run 50 amps off of one cell. You run them in parallel, about 5 or 6 of them, and you multiply that, and you bring it down to a different notch. You add 30 per cell to keep it safe, because remember, they just say it's the maximum continuous. That's going to shorten the life, your cycle life. If it says 800 cycles, they're telling you 800 cycles if you're not running it at that current that they're actually putting on the data. This is just for like appeal. You know what I'm saying? Can it do it? Yes, it can. Will the cell get hot? Yes, it will get hot. Will it get hot enough to thermal shutdown? No. But do you want your cells getting that hot? No. So when you run them in parallel, then you just, you can pull 50 amps continuous or even 100 amps continuous if you have 5 in series, right? Well, 3 times 10 is the 300. So you're safe. 3 times 5, 15. 150 amps. And it's basically, she's still in a safe buffer zone. All right, guys, I'm done with the Chitta Chatta 4000. This is what it is. This is what it looks like. Just know that little thing, you're seeing the explosiveness. You're also seeing the actual chart. It almost burned through. This is, I believe, a 1/8 thickness of steel. This is from my barbecue. And these puppies, this is nice and cool now. This one, ooh, still hot. That one's still hot. That one's still hot. Look at this. Look at the thin copper. See that piece right there? Look how thin this copper is. Basically, it's almost paper thin. This is making the contact. You mean to tell me you expect a lot of current to come out of that little contact right there? It's not thick like a bus bar. Look at it. It's paper. This is literally paper. In fact, I put it on the meter to check the thickness. I guarantee you it's like barely going to read anything. This is all the pieces that came out of there. Look, that's the copper. Can't remember if the copper is the anode and the aluminum is and the anode and the copper is the cathode, because they actually roll them, just like that. They roll them, and obviously they got their paste of the lithium, cobalt, magnesium, right? So they have the copper, the mixture, and then they have a little piece of thin sheeting to separate them, and then they start the other one, which is aluminum with the actual coating on it as well, wrapped up, so you do have liquid. These batteries are liquid. They're not as much as you would do as a lithium phosphate battery, which are actually more liquefied. Hence, they have a pressure valve on top. If they get hot or they get something happens, they overheat, they releases pressure off the top. So somewhat safer versus these bad boys here. They're made in a very tight configuration where that can will not expand. Sometimes they do, and that's a bad sign. Like if you get pouch cells, like cell phones, and stuff that has pouch cells, you don't notice them until you actually notice them. I had an iPhone 3S. I loved it. I had all music on there. And next thing you know, I think it was bulging. And sure enough, the battery went to the point that it starts swelling, it loses capacity, and yeah, it could be very dangerous. These are more confined. So you see when the impact that I did on them. Now, it don't have to be an impact. I can actually, there could be a short. There could be basically a short within the cell, and then it'll automatically start heating up and cause a fire. Once it reaches that thermal point, it's going to catch fire. And then, of course, you got them all lined up together with cell spacers. You got 40 of them, you know, in a pack, 30 of them in a 10S, 3P for 7.5 amp hours. Dude, even the small little scooters for my kid had hers was a 7S 1P, right? Her first little scooter. Of course, daddy exaggerated, you know, there was 18650s pushing 2500 milliamp hours each. So basically it's a 2.5 amp hour battery, right? At 29 volts. Daddy made her a 7S 3P of 21700, 5000 milliamp hour batteries. Yeah, that thing ran great, amazing, until one day it stopped running. So obviously I haven't done a deep dive into that, but I already bought everything I needed just in case if the controller blew, because obviously it was a real small controller, 250 supposedly watt motor. Doesn't matter what size of battery, as long as it's the same voltage, it'll still charge you with a problem. And that's where the problem started, because I would plug it in and the charger was showing green. Basically a charging board, something blew on it. Don't know if it was a cell, don't know if it's a controller. Nonetheless, I got plenty of cells there, and I bought myself a 200, 500 watt controller. And I even got her a throttle with a display. She didn't have one before. I had a whole bunch of lights and a whole bunch of blinkers on it and a horn for her that doesn't come with it. So it'll be a pretty custom little ride when I'm done with it. But yeah, so just like these other ones, the 10S's that I made, they're 15 amp hours. It handled it without a problem. It charged up. Of course, I had those two problems with the charging board. The same identical situation. With a charging board, something blew. I don't know if it was a MOSFET on the charging side, but it actually had voltage in the battery. You know, it was like 30, 36, 37 volts, right? But when you checked the actual charging board, because on those small lengthwise BMSs, and I'll show you what they look like, they have the battery, which basically the positive and negative that goes to your controller, and then they have separate power positive, which they call a C minus, C plus, charging minus, charging plus, separate, you know, that works together with the system, but it's not attached to the actual battery minus and battery negative. So when that blows, that separate MOSFET, a circuit in there, in that board, it stops charging. I try to jump it and put it directly into the battery plus, battery minus discharge, and it blew the charger. And because obviously it was too much voltage going backwards into the battery, the charger, I don't think the charger had, what do you call it? The resistors, what are they called again? Where basically the voltage could go in, but any voltage going backwards is stop. It doesn't have that, which I need to definitely add those inside of all these cheap chargers for safety reasons. If that happens again, bam, you know, obviously the boards go before the charger, but it's for safety reasons. It's always good to add that. I'll get you the name of that correctly. You guys that are definitely technicians, you know all about that. All right, guys. So this is a wrap. It's your boy, Dr. Fix-A-Lot, a.k.a. all about lithium. And you can catch me, you can lock me, you can love me, you can hate me, you can want to talk to me, you can debate me, you can say whatever you want to say, because this is the place that you can say it. All day, expressing what I think. Don't quote me as being professionally perfect. I'm just talking about things that I love, and I'm doing a lot of research, and obviously I might get it wrong, cathode and anode. You know what I'm saying? I really didn't study all that good, but I got the basics down, you know. So I already started building. I started with Milwaukee M18s and M12s, rebuilding those, and you know, that's how I got into it, buying these cheap little spot welders that you connect to a 12-volt battery, 750 cranking amps, and you know, obviously they're cheaply made. They do the job, they heat up, and they can't really do too much spot welding when it comes to serious material like 0.02 millimeter pure nickel. They tack, and of course, they always, with vibration, fall off. And if you really look deep into the original manufacturer, Milwaukee makes them, they look like they're nickel, but they're really copper. They're copper nickel plated. So it's really a copper 0.2 little bus bars they got on those real quick. So kind of doing the nickel, you know what I'm saying? You add more resistance to it. So, but nonetheless, got me to where I got myself a good spot welder. It did phenomenal until it blew the charging board. That's another discussion for our next conversation about the Glitter 811H. Amazing spot welder, but as you start doing research and investigating, you find out that it has a very a fault with they're using budget. I'm going to stay straight up cheap MOSFETs, right? And they had another issue with a spike voltage coming back from the TV transistors, resistors, that, you know, you would get spikes up and down. I believe they kind of addressed that. They have two shunt resistors that obviously, you know, they got 80 MOSFETs, but they're cheap MOSFETs, man. What would it cost them to put some decent, high powerful MOSFETs, you know? You didn't have to use 80, you had to use less of them, and your system would never ever blow. Little small things, you know, first version, second revision, third revision, dude, they're still using the cheap MOSFETs. Then you got a brand called AWITZ, AWITHZ, right? They got different versions. They got the P60, the P20. They got the P90D, and then, which is about close enough to be the Glitter. And then they got the Mac Daddy, which is the P120D, which is 69.6 kilowatts of actual spot welding. That means it doesn't hesitate to do like freaking 0.5 millimeter pure copper without a problem, with stainless steel. I've seen the other guys that do it, you know, they have a channel, a few of them that are pretty interesting, funny, interesting. I find them a comic relief when I watch them. They're Spanglish and everything's pretty cool. But you know, these guys love it, love what they're doing, man, and I respect that for that. But yeah, it's a smaller compact unit versus the Glitter's this big. It actually has 6 2.8 volt, I believe 3,000 or 3,400 capacitors on it, right? And they keep it running at 6 volts, 5.8 volt, right? Discharging 42 kilowatts, goes to 99. I pushed it to 76 with 0.2 pure nickel, then adding 0.2 pure copper, and then adding 0.2 little pieces to make that copper nickel sandwich. Well, the reason why I did that is because it was a 20S. It was 2 packs, 20S 8P, right? And to confine it, you know, I couldn't have this big long battery, so I had to fold it. So by folding it, that's when I added the piece of copper. Originally, I started with just the corner, the folding part, which it did pretty good, but you know, I'm revising that, and that's where it blew. The screen went dark and the freaking smoke started coming out. Sure as hell, I checked the voltage after I unplugged and everything on the actual pens, and it was an open circuit because it was 5.6 volts. You know, it's not supposed to be like that. It's supposed to be like that when you trigger it, and then it blasts that amount with all the capacitors and all the 80 MOSFETs to give you that high discharge. So then I took it apart, found the resistors, they're blown. I did a multimeter with a continuity test and checked the MOSFETs, both sides, and they beeped. I mean, there was continuity where they're not supposed to be none. I did check the TV resistors, transistors, and those were fine. So it's a known problem that they have. And I wish they would address it with an up and improved control board, because it's not a one-off. This is happening to a lot of people with heavy use or medium use, or whenever they're welding and they're welding copper, which they claim that you can do it. They claim that you can do 0.5 on copper and nickel, right? So if they're claiming it, then you better be able to handle it, right? And yeah, that happens. It's got a small little fan for the back power supply. It's a decent looking machine, I think so. I thought I had the new version. The board said 08/23/26. Mind you, I bought this on December 02 of 2025. I ordered it, and I actually ordered it from Banggood because AliExpress was a lot expensive. eBay was way expensive, and Amazon, forget about it. At the time, it was like, I was looking for the high capacity. I don't think at that time, AWiz, they didn't have that 120 or the 90. They were still running the 20, the 40, I'm not sure, the 20 or 60, right? But and it's trippy because they're running 3.0 volt capacitors, 3,000 farad capacitors. So they're using 4 in series, right? Versus these guys are using 6, 2.8, 3,400. Obviously, the other capacitors are better quality. I believe they're Maxwell. I'm not sure. Don't quote me on that, but they're decent. And it's a more compact system. But if based on the information you're getting, they have real high capacity, high current MOSFETs, and they don't have problems. They have a little situation where you have to give it a little time. But it's the same thing with the glitter. Which you spot weld. You got to let that, it gives you a clicker like 0.2, 0.3, 0.5, 0.8. How many times? You got to let it rest, then let it fully recharge again, because it works best when it's fully charged. It's slowly charging all the capacitors back up. It doesn't take long. And then you keep going. The pens are pretty thick. They're 50 millimeters thick. That's another thing I don't like about them, because they have like a spring load, and you got to really press hard. My other spot welders just made contact, and just the power zapped those two pieces of metal together. This one you have to press hard, which is not really good because you're pressing hard enough. And I'm a big guy, so I'm going to freaking exaggerate. That's where I had a couple of issues with my cells. Either I freaking pushed too hard and blasted through the cell, and you might as well call it a day with that. All right, that's enough chitter chatter. We'll catch you with the experience, or right now I contacted glitterwelder.com. The person that responded to me said, hey, no problem, we'll have a problem replacing your charging board. I hope they have a new revision. I'd like to talk to their engineering department and be like, listen, man, I like your product. I just wish that you fix the problem, because it's really looking bad for your business, and these other people are taking up a slack. There's different versions. They got the Heltec version, which is a cheaper version, and they have Sunoco, which is the same company basically. Capacitors are not the top grade, but they're decent. They do the job. They cut a lot of corners. When you cut a lot of corners, things happen. So that's that, guys. So in the meantime, in between time, keep your minds open. I know that a lot of people like to use that other one that's pretty decent, that comes with the bus bars open. You can actually buy a pre-made 3D print plastic. I believe it runs with Arduino. But dude, you look at those pens, they're not thick enough, and people that use them, they get hot. So that's for people that are going to do 1 or 2, 3 spot welds, maybe one battery pack within a certain hour period, because you can't continuous soldering on that, and to get to a good soldering point, you need a high capacity spot welder to be able to do, copper, because copper, what happens is copper, you spot weld it, and, copper is so conductive that it spreads the heat real fast. That's the problem. You hit it, bam, and no matter what the power goes, you hit it, and it stretches out through the whole sheet or the bus bar. That's why you have to put a piece of nickel and then hit it with the spot welder. The nickel acts as a short. It shortens that so it doesn't spread out, and it goes straight, bam, makes that contact instantly. So high powerful spot welders are good. And also, if you're getting into those welding onto aluminum, you have some lithium phosphates that use aluminum bus bars, you know what I'm saying, and even the new Eve 46950 or the BYD 4680, which is really a lipo, and the Lakota, whatever, has a 46950, but there are 30 milliamp hours. The cells are made completely different, like on regular 18650s, 21700s, 26650s. Those all have the cylinder, which is all the negative. The bottom, obviously, is the negative. The top, you have the positive. So literally, you have one little plastic ring that separates that positive. That's why we put fishing tape on top of it, because when you're spot welding, you tend to, get close. It's kind of hard to get that little small ring versus that big side of basically looking at this. See? You can see the ring right here. You see it? The separation, can you see it? Right there, you can see it. This cap right here, I'll remove it so you can see it. The back side is all, you can spot weld, Obviously, they really don't want you to spot weld in the middle, because in the middle is where they have that connection. So we'll find out with those other cells, but I'm gonna remove this top here. You peel this off right here, peel it this way, you pull off this, and underneath is the SDI chip, or SID, which is basically a safety mechanism. What it does is kind of like a fuse. If something happens, boom, it cuts off, and that's probably what happened to those cells, because they're perfectly fine, which was this one right here in my hand, which I, went off like a skyrocket. This one was just my spot welding. You can see I spot welded and I blasted a hole through it, and it ended up draining my first 20S build. I actually had 3 of them, and 2 of them really, but one maybe, but I just took out the 3 because they were pretty hot, because one battery was just sucking and drawing from the rest of the battery pack. I replaced them, and of course, again, when I put it back together, I gotta add a little more, and I added to a complete different cell. It had nothing to do with the 2 with 1 that went bad over here that caused the problem. And then over here, when I tapped it, I went bam, and I hit it, and it went past the actual, and it made messed up the battery. It caused an internal short inside. It started freaking out. Now I figured that one out because I was testing the batteries, checking every series, checking every parallel, and they all had the voltage. Some of them were a little bit lower voltage until, remember, this is a dual pack. This is 20S 8P, making a 20S 16P folded together. I had to take that apart. I already soldered the top to connect them again. Unsolder it, take off the fishing tape, take off all the damn cap down freaking tape that I did, right? But just a living learning curve. You got to take your time, do it right, do your measurements, make sure you're doing, this is a big move for me, not only building the battery pack, because I built 2 battery packs that were perfect until I made that fold. That becomes a little more complicated, more complex, and just kept spot welding because I wasn't sure, because remember I added 0.2 W-shape nickel for the offset spacers, first time using those, and since I really didn't figure it out how I was going to do it, I could have done it all the way across and then folded that. It would have been better. But I wanted a little bit more contact, and I had to add copper because it's going to be pulling high current. Not really the whole 116p. That'll definitely, the cells are rated for, I believe, 20 amps continuous discharge. That's basically 320. Remember I told you about the medium, that gray area? It really is going to push about 15 or 10. So 10 at 16 would be 160 amps. I got two 50 amp controllers, that's 100 amp. So I was way under the threshold, and the BMS was a JK 2A 20S 20P, which basically 2 amp active balancing, it's 20S for how many strings you got, and it's a 200 amp 360 peak BMS. Excellent BMS, because all the other ones don't really offer a real active balancing, inductive or capacitor, where they transfer the energy back and forth. That prolongs the battery life. The JBD is a decent build. I love it. It's amazing. It's nice and thick. I have a few of those as well, all different versions of them. And I also got, who else do I got? We got JK BMSs. We got Jabata, JBD, and there's one more I have there. My point is, like even Ant makes phenomenal BMSs, but they have passive balancing. So basically, if you ever built a small little boards for a 3S battery pack, you'll see that they have a whole bunch of MOSFET resistor diode slash, and what it does is just maintains with a small little MCU unit, microcontrol unit that tells it, hey, you make sure the cells are this, all of this, but it doesn't keep them all equilibrium. Even the Milwaukees, the DeWalt's, Ryobi, they don't really have that. They just keep them fairly simple and same. Hence the reason why they tell you to put the same voltage batteries. The same, like if they're brand new, make sure they're all the same voltage. You don't want to have the fluctuation. And as time goes by, you'll see they'll drift. Sometimes they'll drift apart completely. One will have 4.1 volts, the other one will have 4.0, the other one will have 3.9 within that 5S series. And that is what starts killing your battery pack. Premature degradation. So why? You know why they don't add an active balancing to them? Because then your battery lasts 10 times longer. They want you to come back after that warranty period of 1 year goes by. So, guys, it's just a freaking business scam. They make you keep coming back. It's like back in the days, they made cars that last forever. Dude, the metal, there's still like 40s and 50 cars out there. The freaking metal's exquisitely strong. Steel frames, steel bumpers, steel everything, fenders, the whole nine. You hit anything, everything else is gonna break except for the car. You get what I'm saying? The engines were diehards. You run them until freaking 200,000, 300,000, up to 1,000,000 miles, some of them, if you maintain them correctly. Now they build them out of plastic. They call it the crumple zone. So the freaking car is supposed to it's supposed to absorb the impact. But while it's absorbing the impact, you totally lost your car. It's totaled because you can't repair it. So same way with these guys. They're going to build you something that's going to last forever. You're only going to buy it once, right? It's a stupid way to do business. I understand the business model, but man, build good products. Give me customers. These things have a shelf life and a recycling life. Basically how many discharge and charges they have already. And they are keeping them at a safe voltage. You're not running them down to 2.5 and they're not charging them at the 4.20. So they're keeping them good. That's why you can fully charge them and leave them and not worry about them. Oh my God, self-draining, because that's what happened when you fully charge a lithium cell. That cell is at the freaking top point. Just think about a freaking boxer or a racer. He's ready, he's racing. He's about to run, but he ain't going nowhere. That's what's happening inside of the cell. The chemistry is fully charged and it ain't going nowhere. It's supposed to go somewhere, it's not going anywhere. It starts going backwards. That's where the dendrites start building up. That's where you start getting degradation, early premature battery failure. So that's the reason why. So, and BMS is amazing because they push high numbers, nice built, solid piece, but they don't have active balancing. JK does amazing, but I believe that the highest they go is 200. I think no, they go 300. I know for their big lithium phosphate cells, they go 300. I think they also do 300 as well on their other smaller units, 17 to 24S. But same thing with JB does the same as well, JBD. Ant's the only one that pushes it up to 420, which is like 1,000.50 peak. There's other BMSs that are actually, I was watching one that was impressive. It had 8 amps continuous active balancing. Now, I was like, wow, this is a new one. I like this one. But then you look at the actual bus bars, right? The battery negative, the battery the P minus and P plus wires. They're like literally, they only have small connections. Like, you know what I'm saying? It doesn't look like you could put a thick, if you're pushing that much, and they will go up to 300, I believe 300, 400. It's a decent. It's like I believe a derivative of JK BMS. They're usually all made by the same people. Just rename it. JBD makes them freaking. I'm looking at them. They have an amazing bus bar. A freaking solid piece of copper running across. They're actually using the new modern MOSFETs, which are more powerful. JK still using the older model, which are true and diehards, like the, can't think, I got them inside the house. I'll show you the MOSFETs. They're decent and they're good MOSFETs, but the ones they're using on the JBD are freaking more powerful. They can handle so much more, and that's what you want, so you don't have a problem blowing. But they don't have an active balancing. They have passive. And to me, that's important. Other people doesn't care because they're just going to run their batteries and charge them. I don't think anybody's going to go out there and buy themselves a separate, wired up with series so you can plug in actual, which is what I would do. I actually bought the actual balancer, and it goes to 17S, and it's all capacitors, 6 amps charging. Don't like it. Doesn't have an app. It's a simple thing. You know what I'm saying? We'll see how it works. But JK does also sell them to like 2 amp, 4 amp, 6 amp, 8 amp, but individual actual balancing piece of board besides their BMSs that go up to 2 amps. They go 2 amps. The other ones go 0.06 amps and 0.4 amps balancing on theirs. Pretty much all of them. They have some type of balancing. And I know how important that was to me when I built that 20S 16P. I had 30 cells that I was checking, right, doing capacity tests on them. And when I charged them back up, I didn't charge them to the original 3.65 volts. I think it was 3.73. So I had a real deviation between some cells there. It took a while to actually balance. And that's when I started running into a problem that I was like, I checked it. It was like, oh, it was a 0.09 of deviation. It got that low. I was like, oh, that's pretty good. And I came the next day, I left it on the charger, watching it, and came back the next day. It went to 0.23. Then I seen a whole row of cells, 17, 18, and 19. Everybody else was at 4.18 volts, and this one was 4.8. I was like, what the hell? That's when I want the problem. And back to what I was telling you, how I figured out, I did all the testing. I couldn't find any dead cells, but then I happened to lean my hand on one of the cells, and holy crap, it was hot as hell. I got the thermal reader, bam, put it on there. I was like, oh, this thing is 103. Checked everything else, it was fine. So I noticed that was a short. Again, one of my cells that I over spot welded. You only need, if you're doing a good spot weld on the positive, 2 is good, 4 is enough. On the back, it's the same thing. You don't need to. Like me, I'm like, oh, the more spot weld, the more connection. Dude, it's not the way it works. Just think about what we just pulled apart and these pieces of little thin copper making the cathode or anode, and then the aluminum. When I take this battery apart, I'll show you exactly what I'm talking about. So, you know, it'll do it with copper, a little more, pure nickel, 0.2. I think it's perfect, because I see these guys building packs in China all day long, and they're using 0. For big 72 volt batteries, they're using 0.15, 0.015 millimeter pure nickel. And then what they do is on the actual positive connection, negative connection, they double up on that area there. You know, other people say that, you know, really when you're doing the series connection, that's where you're pulling the most amperes out of the battery. You should do it there. I think you could do it just start off with 0.15, put 0.2 copper and little pieces. That should be enough. But, you know, it all depends on your battery and its configuration and how you fit it, because try to get that 10 millimeter, 0.2 millimeter by 10 millimeter strip in this zigzag pattern, you're running into problems, which is what happened to me, where every time I was, first of all, I was getting shocked all over. Like, what the hell? I'm getting shocked. The more I was putting together, the more volts are going through it. You have to cover up the battery while you're working on it. You know, I'm learning, baby. It's how it is, man. But, you know, it's all fun and games, but this is serious business. So as I go through the experiences and the curves, I have no problem showing you my F-ups. You know what I'm saying? This is an F-up. All right, that's it. No more talking, because I'll keep going on for hours and days and days. Bada bing, bada boom, it's your boy, and I'm out of here. Yikes.